This video explores the topic of predictive maintenance within the framework of the European project titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. There are three main maintenance strategies for industrial machines. The first is run to break, where a machine is operated until it fails. This approach maximizes operating time between shutdowns, but failures can be catastrophic. Breakdowns may cause severe machine damage, safety risks for workers, long production downtime, and very high repair costs. The second strategy is preventative maintenance, performed at fixed time intervals that are usually much shorter than the actual machine lifetime. Its main advantages are easy planning and a reduced risk of catastrophic failure. However, many machines are still fully functional when maintenance is carried out, leading to unnecessary repairs, premature component replacement, and increased costs. The third strategy is predictive maintenance, which uses continuous condition monitoring to predict failures. Defects are detected early, and maintenance is performed only when needed, just before failure becomes likely. This approach prevents failures while avoiding unnecessary replacement of functional components. It relies on reliable condition monitoring and fault detection techniques based on extensive sensor usage. Due to its growing importance across many industries, the following slides focus on predictive maintenance. Several techniques are used for machine condition monitoring and fault detection, including vibration analysis, lubricating oil analysis, acoustic noise analysis, high-frequency ultrasound emission, performance analysis, and thermography. Among these, vibration analysis is the most widely used. Machines generate characteristic vibration patterns during both normal operation and faulty conditions. Each machine has a unique vibration signature related to periodic processes, such as shaft rotation, gear meshing, bearing motion, and electromagnetic field rotation. These processes appear at specific frequencies in the vibration spectrum, allowing the vibration source to be identified. Vibration analysis employs various methods, with frequency domain techniques being the most common, alongside time domain methods and time-frequency approaches such as wavelet analysis. It enables defect detection at very early stages. Vibrations are typically measured using accelerometers mounted on the machine's surface. Results of vibration analysis are available almost immediately. Thanks to extensive practical experience and advanced analysis tools, vibration analysis is the dominant technique in modern predictive maintenance. The next diagnostic technique is lubricating oil analysis. As defects develop, friction and wear increase, generating microscopic particles, typically up to about 10 microns, that accumulate in the lubricant and are captured by filters. These particles are then analyzed by their quantity, type, shape, and size to determine whether a defect is present and what kind it is. Unlike vibration analysis, which provides near-instant results, oil analysis usually requires several days of laboratory processing and often cannot precisely locate the defect. For example, when multiple bearings are made of the same material, detected particles indicate that a bearing is failing, but not which one. Vibration analysis, in contrast, can identify the exact fault location based on characteristic vibration patterns. For this reason, vibration analysis generally offers greater diagnostic capability, while oil analysis remains a valuable complementary technique. Another important diagnostic method is acoustic noise analysis. Machine noise is recorded using microphones placed at a distance from the machine. Unlike vibration sensors, which must be mounted directly on the machine, microphones allow remote measurements. This is particularly useful when direct sensor installation is impractical, such as in environments with extreme temperatures, high pressure, humidity, or aggressive chemicals. However, vibration analysis is more sensitive, as it measures directly on the machine's surface and can detect very early-stage faults. Acoustic analysis can identify more advanced defects that generate strong noise. Also, acoustic analysis is susceptible to ambient environmental sounds, which can reduce diagnostic accuracy. High-frequency ultrasound emission is a relatively new condition monitoring technique that has gained increasing attention. It is based on the generation of high-frequency mechanical waves during the initiation and growth of defects, such as crack propagation. In metallic components, these waves typically range from 100 kHz to 1 MHz or higher and are detected using piezoelectric sensors mounted directly on the machine surface. Because the waves propagate through the material rather than through air, they cannot be measured remotely with microphones. The main advantage of this technique is its ability to detect crack initiation and early-stage defects, often earlier than vibration analysis. However, a key challenge is the requirement to measure very high frequencies. Performance analysis is another diagnostic approach that can provide clear indications of specific faults. For example, reduced intake power in a reciprocating compressor may indicate a blocked filter, while reduced power output in an automobile engine may point to a malfunctioning cylinder. Thermography is a non-contact technique used to measure temperature distribution in machinery. Localized temperature increases reveal elevated friction and wear, which may indicate developing defects. Its main advantage is non-contact measurement, but it typically detects faults only at later stages, reducing the time available for maintenance planning. A significant time often passes between the initial formation of a defect, such as a microcrack, and catastrophic failure. This gradual development allows defects to be detected using diagnostic techniques and repaired before failure occurs. The figure shows the progression from defect initiation to catastrophic failure and indicates when different diagnostic methods can detect the fault. The goal of condition monitoring is early defect detection, which provides enough time to plan maintenance, reduce repair costs, and minimize production downtime. Among the available methods, high-frequency ultrasound emission and vibration analysis offer the earliest detection, enabling timely repairs and component replacement. Rotating machinery is prone to various faults. In the following slides, we review the most common defects and show how vibration analysis can be used to detect them reliably. The analysis is mainly performed in the frequency domain using vibration spectra obtained by the fast Fourier transform. The first fault considered is unbalance, which occurs when the rotor's center of mass does not coincide with its axis of rotation. Unbalance can result from rotor eccentricity, manufacturing defects, material inhomogeneity, corrosion, shaft bending, uneven thermal expansion, or the accumulation of dirt and deposits. During operation, unbalance generates centrifugal forces that excite the shaft bearings, where vibrations are typically measured. Several types of unbalance can be distinguished. Static unbalance exists even when the rotor is stationary. In this case, the weight distribution axis is parallel to the rotational axis. Couple unbalance occurs during rotation when the weight distribution axis intersects the rotational axis. Dynamic unbalance is a combination of static and couple unbalance and is the most common type of unbalance, which typically occurs in long rotors with a length much greater than their diameter. The rotational axis neither intersects nor is parallel to the weight distribution axis. Another form of imbalance appears in overhung machines, where components such as fans or propellers are mounted outside the supporting bearings. All types of imbalance produce a dominant vibration at the shaft rotational frequency, with amplitude increasing with the square of rotational speed. This vibration is mainly radial in both horizontal and vertical directions, while axial vibration is usually low, except in overhung rotors. Pure imbalance does not generate higher harmonics. Their presence usually indicates other problems, such as misalignment or mechanical looseness. A 90-degree phase difference is typically observed between horizontal and vertical vibrations at the same bearing. Because all unbalanced types produce strong vibration at the shaft rotational frequency, the specific unbalanced type is identified by comparing vibration amplitudes and phase angles at both bearings. Static unbalance shows equal amplitudes and zero phase difference. Couple unbalance shows similar amplitudes with a 180-degree phase difference, and dynamic unbalance shows differences in both amplitude and phase. It is important to note that imbalance is not the only cause of vibration at the shaft rotational frequency. Faults such as misalignment, bent or cracked shafts, eccentricity, rotor bar defects, rubs, belt problems, mechanical looseness, and resonance can produce similar effects. Therefore, reliable diagnosis requires additional indicators, including phase relationships, amplitude distribution between bearings, harmonic content, vibration direction, and speed-dependent behavior. The next type of defect in rotating machines is shaft bending, which may result from excessive heat, external mechanical loads, or an overly long shaft. It is typically characterized by increased axial vibrations, with a dominant peak at the rotational frequency when the bend is near the shaft center. If the bend is closer to the shaft ends, the second harmonic also becomes prominent. Axial vibration measurements at the two end bearings show a 180-degree phase difference, while measurements at different locations on the same bearing remain in phase. Shaft misalignment occurs at the coupling between two rotating machines, such as a motor and a pump. Perfect alignment, where the shaft axes are both parallel and intersecting, is rarely achieved, leading to two main types of misalignment, parallel and angular. In parallel misalignment, the shaft axes of two machines are parallel but do not intersect. This condition produces increased radial vibrations, with spectra containing the first, second, and third harmonics of the rotational frequency. Notably, the second harmonic may be larger than the first. In angular misalignment, the shaft axes intersect but are not parallel. This results in increased axial vibrations, with the dominant component at the rotational frequency and smaller second and third harmonics. In practice, most machines exhibit a combination of both misalignment types. Common causes include improper installation, thermal expansion, and foundation movement. Many rotating machines, such as fans, pumps, turbines, and compressors, contain vanes or blades mounted on the shaft. Their vibration spectrum typically shows a dominant peak at the vane pass frequency, defined as the number of vanes multiplied by the shaft rotational frequency, along with its harmonics. An increase in the vane pass frequency amplitude usually indicates internal wear, erosion, or increased air entrainment. Elevated harmonics of this frequency may point to impeller damage, flow recirculation, or cavitation. A strong component at the shaft rotational frequency suggests mechanical issues such as unbalance or misalignment. If one or more vanes are damaged, impulsive vibrations occur once per shaft revolution as the damaged vane passes. These appear as mid-frequency harmonics of the shaft rotational frequency. Although such defects are difficult to detect directly in the spectrum, cepstrum analysis, discussed later, enables reliable identification. The next type of defects we will consider are rolling bearing defects. Rolling bearings are essential components of rotating machinery and are the most widely used bearing type. They are classified by the shape of their rolling elements, such as ball, roller, or needle bearings. Each bearing consists of an inner ring, an outer ring, and rolling elements between them. Typically, the outer ring is stationary, while the inner ring rotates with the shaft, providing low friction motion. The bearing geometry is shown in the figure. Rolling bearing defects can result from excessive loads, poor lubrication, improper installation or handling, contamination due to inadequate sealing, or insufficient internal clearance. Damage may occur on the outer ring, inner ring, or rolling elements, and commonly includes fatigue cracks, spalling, wear, indentations, corrosion, and other surface damage. Under cyclic operating stresses, material fatigue leads to crack initiation. As rolling elements pass over these cracks, they grow and eventually cause material removal, known as spalling, which can ultimately lead to bearing failure. The figures in the first row illustrate the progression of damage in a rolling bearing over time, while the remaining images show different types of bearing damage. 4 characteristic frequencies are commonly used in rolling bearing analysis. The ball pass frequency of the inner ring describes how often rolling elements pass a fixed point on the inner ring, while the ball pass frequency of the outer ring refers to the frequency at which rolling elements pass a fixed point on the outer ring. The ball spin frequency represents the rotational speed of each rolling element about its own axis, and the fundamental train frequency defines the frequency at which the rolling elements complete one full revolution around the bearing raceway. All of these frequencies depend on the bearing geometry and dimensions and can be calculated using the formulas shown on the slide. Each time a rolling element passes over a defect, it excites the bearing at its resonant frequency, generating high-frequency vibrations, typically in the tens of kilohertz. This resonance depends on the bearing's material, geometry, load, and operating speed, and it repeats periodically as the rolling elements pass the defect. The overall vibration signal contains contributions from different sources. In the time domain, it consists of a dominant low-frequency component caused by imbalance, misalignment, or shaft bending, with small, superimposed high-frequency impulses from bearing defects. The first figure shows a vibration signal caused by an outer ring defect, where each rolling element produces an impulse that repeats at the ball-pass frequency of the outer ring and is superimposed on the shaft rotation frequency. In the frequency domain, early bearing defects appear as a high-frequency haystack, while low-frequency peaks correspond to the shaft fundamental frequency and its harmonics. However, the presence of a haystack alone does not confirm a bearing defect, since similar patterns can arise from gear faults or random sources such as wear or flow-induced vibrations. To distinguish between random and periodic high-frequency excitation, identify whether the haystack originates from bearing or gear defects, and, if a bearing fault is present, determine whether the outer ring, inner ring, or rolling elements are affected. The envelope spectrum of the signal should be analyzed, as will be explained later. The vibration spectrum of rolling bearings depends directly on the extent of damage. In a healthy bearing, the spectrum contains only low-frequency components at the shaft rotation frequency and its lower harmonics, caused by effects such as unbalance, misalignment, or shaft bending. No bearing-related frequencies are present. In the earliest stage of damage, the first observable feature is the high-frequency haystack. Detecting this pattern and applying envelope spectrum analysis allows very early fault detection. As the damage progresses, characteristic bearing frequencies, such as the ball pass frequency of the inner ring, the ball pass frequency of the outer ring, and the ball spin frequency, along with their harmonics, appear in the mid-frequency range. In the advanced stage, severe defects generate predominantly random vibrations, which raise the overall noise level of the spectrum. In summary, the vibration spectrum can be divided into three regions. The low-frequency range, with shaft rotation frequency, and its lower harmonics is caused by shaft-related defects like imbalance, misalignment, or bending. The mid-frequency range, containing characteristic bearing frequencies and their harmonics, often with modulation sidebands, indicates developing damage. And the high-frequency range is characterized by the haystack pattern typical of early bearing defects. The next important type of defect in rotating machines is gear defects. Gears are complex mechanical components and can vary significantly in size, which means they operate at different rotational speeds. Smaller gears typically rotate at high speeds, up to several kilohertz, while larger gears rotate much more slowly, sometimes only a few hertz. Therefore, vibration sensors with a wide frequency bandwidth are required to capture both low and high-frequency vibrations. Common gear defects include wear, damaged or broken teeth, misalignment, and backlash. A key parameter in gear vibration analysis is the gear meshing frequency. In a healthy gear system, only the meshing frequency appears in the vibration spectrum. When defects are present, variations in amplitude or frequency occur, leading to amplitude or frequency modulation, which appears in the spectrum as sidebands around the meshing frequency component, and its harmonics. Also, harmonics of meshing frequency appear in the spectrum, each surrounded by its own modulation sidebands. In addition, vibrations may occur at the gear's natural resonant frequency, which depends on the gear's material and geometry. Although this frequency is not known in advance, the appearance of a new broad spectral component with sidebands is a strong indicator of resonant frequency. This slide shows vibration spectra for common gear defects, including gear eccentricity, tooth wear, excessive tooth loading, misalignment, and broken or cracked teeth. A defect on a single gear tooth can spread to the mating tooth and gradually affect multiple teeth on both gears. Gears with prime number tooth counts tend to have longer service life because defects are distributed across all teeth. When the tooth counts are not prime, damage is concentrated on fewer teeth, leading to more severe damage. Another important parameter is the gear assembly phase frequency. When teeth are damaged, vibration components appear at this frequency and its harmonics. If a specific pair of teeth on both gears is simultaneously damaged due to transport or assembly, elevated vibrations occur each time they mesh. This engagement frequency, known as the hunting frequency, appears in the low-frequency region of the spectrum. We will now discuss vibrations in electric rotating machines, such as motors and generators. In these machines, vibrations arise from both mechanical sources, like imbalance, misalignment, and bearing defects, and electromagnetic forces. This section focuses on alternating current machines, as they are the most commonly used. Alternating current machines are either synchronous or asynchronous. In both types, the stator generates a rotating magnetic field whose speed, called the synchronous speed, depends on the number of magnetic poles. In synchronous machines, the rotor rotates exactly at this speed, while in asynchronous machines, it rotates slightly slower. The stator is made of a laminated steel core to reduce eddy currents and heating. Coils carrying alternating current, 50 Hz in Europe and 60 Hz in the United States, produce magnetic poles. The stator always has an even number of poles, half of them north and half south, arranged alternately. With 2 poles, the magnetic field completes 1 full rotation per current cycle, so the synchronous speed equals the line frequency. With 4 poles, the field rotates at half that speed. In general, increasing the number of poles reduces the rotational speed of the magnetic field. The pole pass frequency is the rate at which magnetic poles pass a fixed point on the stator. It is always twice the line frequency, 100 Hz in Europe and 120 Hz in the United States. In vibration spectra, electrical machines typically show a strong component at twice the line frequency, caused by effects such as magnetostriction, defects, or air gap irregularities. By contrast, a strong component at the fundamental line frequency usually indicates a measurement issue, most often ground loop interference. In the synchronous motor, the rotor has its own magnetic field, produced by permanent magnets or DC excited windings. This field locks to the stator's rotating magnetic field, so the rotor always runs at synchronous speed. Changes in load do not affect speed. Instead, they change the phase angle between the rotor and stator fields. In other words, load variations cause phase modulation, not speed variation. The shaft rotational frequency is therefore equal to the synchronous speed. For a 2-pole motor, this speed equals the AC line frequency, so the shaft rotates at line frequency. Electrical effects generate vibrations at twice the line frequency. Mechanical defects, such as rotor eccentricity, also produce vibrations at the second harmonic of the shaft rotational frequency, which is again twice the line frequency. As a result, electrical and mechanical sources can excite the same frequency, making them difficult to distinguish. One way to separate them is by increasing the electrical load. Electrical vibrations increase with load, while mechanical ones remain nearly unchanged. Another method is to shut down the motor. Electrical components disappear immediately, whereas mechanical vibrations decay gradually. Finally, synchronous motors may also exhibit increased vibration due to stator winding looseness, which raises the vibration level at the coil pass frequency. In asynchronous, or induction, motors, the rotor has no permanent magnets. Instead, it consists of a cage made of conducting bars connected at both ends. When the stator's rotating magnetic field acts on the rotor, currents are induced in these bars, creating the rotor's magnetic field through electromagnetic induction. The rotor also contains a laminated steel core, which completes the magnetic circuit and reduces eddy current losses. The interaction between the stator and rotor magnetic fields produces torque, causing the rotor to rotate. Although the rotor attempts to follow the stator's magnetic field at synchronous speed, it always rotates slightly slower. The difference between synchronous speed and rotor speed is called slip frequency, which increases with load. Typical slip frequencies are very small, up to about 0.003 Hz at no load, and up to 0.5 Hz at full load. In induction motors, stator defects also generate a vibration component at twice the line frequency. Distinguishing electrical from mechanical defects is somewhat easier because the second harmonic of rotor speed is slightly lower than twice the line frequency. However, this difference is very small and requires spectrum zooming techniques to be clearly identified. Rotor defects in induction motors typically appear as modulation sidebands around the shaft rotation frequency and its harmonics. The modulating frequency equals the slip frequency multiplied by the number of poles. The left figure illustrates the spectrum caused by cracked or broken rotor bars. The right figure shows the spectrum for insulation defects between laminated rotor sheets. In the following part of the presentation, we will discuss vibration signal analysis techniques. The most commonly used approaches are frequency domain methods, although time domain techniques are also applied. Vibration analysis may include parameters such as RMS and peak factor, statistical measures, and phase differences. We will focus on 3 widely used techniques: envelope spectrum, cepstrum, and kurtosis. We begin with the envelope spectrum technique. Defects in rolling bearings or gears generate a high-frequency haystack in the vibration spectrum, which is most clearly observed in the acceleration spectrum and is particularly useful for early fault detection. This high-frequency haystack may be caused either by defects or by random vibrations. Defect-related haystacks exhibit a periodic structure, reflecting the regular motion of machine components, whereas random vibrations produce a non-periodic structure. To determine whether a defect is present and to identify its type, the structure of the high-frequency haystack must be analyzed. However, analysis in the time domain or frequency domain often does not provide clear diagnostic conclusions, as shown in the figures. To analyze the high-frequency haystack, the envelope spectrum technique is applied to the vibration signal in the time domain, which is shown on the right. This method involves 4 steps, which are explained using the example of a rolling element bearing with an outer ring defect. The first step is bandpass filtering, which isolates the high-frequency haystack. The second step is rectification, which takes the absolute values of the filtered signal. Third, the signal envelope is formed. Finally, the last step is the calculation of the envelope spectrum using the fast Fourier transform. In the case of an outer ring defect, the envelope spectrum shows the ball-pass frequency of the outer ring and its harmonics. In contrast, random vibrations produce a non-periodic envelope spectrum. The next important vibration analysis technique is cepstrum analysis. It is computed in 3 steps. First, the Fourier transform is applied to the vibration signal to obtain the vibration spectrum. Second, the logarithm of the spectrum is taken. And finally, the inverse Fourier transform is applied. The term cepstrum is derived from reversing the first part of the word spectrum, reflecting its origin as the inverse Fourier transform of the log spectrum. Cepstrum results are expressed in quiffrency, a time-like parameter whose name is formed by reversing the word frequency. Cepstrum analysis is particularly effective for detecting harmonic families in the vibration signal. In the frequency spectrum, weak harmonics may be hidden by dominant components. Taking the logarithm compresses the dynamic range, making these harmonics more visible. The inverse Fourier transform then produces the cepstrum, where a clear peak at the corresponding quiffrency reveals the fundamental frequency and its harmonics. In vibration spectra of certain rolling bearings and bladed machine defects, harmonics are often present but difficult to detect directly, making the identification of the fundamental frequency challenging. In such cases, cepstrum analysis is a highly effective diagnostic tool. This is demonstrated using 3 examples: a rolling bearing defect, a steam turbine defect, and a gear defect. In the first example, a rolling bearing defect produces very low amplitude harmonics that are almost invisible in the raw spectrum. Applying a logarithmic transformation compresses the amplitude range, making these harmonics visible. The inverse Fourier transform then yields a cepstrum with clear peaks at 4.84 milliseconds and its multiples. This corresponds to a fundamental frequency of 206 Hz, identified as the ball-pass frequency of the outer ring, indicating an outer ring defect. In the second example, a steam turbine with a broken blade shows only minor changes in overall vibration, but generates a family of harmonics at the shaft rotational frequency of 50 Hz in the mid-frequency range. While these harmonics are difficult to detect in the spectrum, cepstrum analysis reveals peaks at 20 milliseconds and its multiples, clearly identifying the fundamental frequency as 50 Hz. The third example involves a simple system with 2 gears. The driving gear has 42 teeth and rotates at 68.57 RPM, while the driven gear has 72 teeth and rotates at 40 RPM. The gear meshing frequency is 48 Hz. We consider 2 scenarios, a defect-free system and one with a gear defect. Comparing the time domain vibration signals shown in the figure, the blue signal for the healthy system and the orange signal for the faulty system, shows that time domain analysis alone cannot reliably reveal the presence or type of defect. The same limitation is seen in the frequency domain, where spectra do not provide clear features to identify the defect. However, cepstrum analysis shows a clear peak at a quiffrency of 0.02083 seconds, corresponding to 48 Hz, the gear meshing frequency. This clearly indicates a gear defect. These results demonstrate that cepstrum analysis can detect gear faults even when time domain and frequency domain analyses fail. The next commonly used technique in vibration analysis is kurtosis. Kurtosis measures the peakedness and tail behavior of a vibration signal's probability density function. Higher values indicate sharper peaks and a higher likelihood of large amplitude events. For example, the vibration of a gearbox or rolling element bearing without defects shows low amplitude oscillations and no pronounced impulses, resulting in a low kurtosis value. When a defect is present, like a damaged bearing race or a broken gear tooth, periodic high amplitude peaks appear in the signal. Each peak corresponds to a rolling element passing over a defect or a damaged tooth engaging, producing impulsive vibrations. These increase the occurrence of large amplitude events and therefore the kurtosis. The more severe the defect, the higher the kurtosis value. Therefore, an increase in kurtosis can serve as an indicator of fault presence. However, it does not reveal the defect's type or location. For that, complementary techniques like spectral analysis, envelope spectrum analysis, or cepstrum analysis are required. This slide shows two vibration signals. The first, on the left figure, is from a defect-free system. Amplitudes are small, below 0.6, the probability density function is broad, and kurtosis is low at 3.9. The second signal, in the right figure, corresponds to a ball-bearing defect. Here, amplitudes reach up to 6. The probability density function is sharply peaked, and kurtosis is much higher at 14. This clearly shows that an increased kurtosis indicates the presence of a defect. In this tutorial, we've covered several important aspects of predictive maintenance. First, the basic concept. Predictive maintenance involves continuously monitoring the condition of machines using sensors. This data is then processed using advanced techniques, or AI models, allowing us to detect faults and defects at an early stage. Next, the benefits. By detecting problems early, predictive maintenance can save significant maintenance costs, prevent catastrophic failures, and give enough time to plan repairs and secure replacement parts. We also looked at the techniques used. The most common approach is vibration measurement and analysis. However, other techniques are also important, including noise measurement, lubricant oil analysis, performance analysis, high-frequency ultrasound, and thermography. Then, we explored applications of vibration measurement and analysis. These techniques can detect unbalance, shaft bending and misalignment, vane-related defects in rotary machines, rolling bearing defects, gear defects, and faults in both synchronous and asynchronous electric machines. Finally, we introduced vibration signal analysis techniques, such as the envelope spectrum, cepstrum, and kurtosis. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.